So please welcome to the stage, Mike.
The questions bit.
Mike's not going to do a Q&A at the end. So questions that you've got, please, you can drop them in Slack, and will get back to you and answer them directly one-to-one on Slack. Cheers.
Thanks a lot, Paul, and thank you everyone for coming today. Although at least I assume some of you out there, as people have probably mentioned on this stage before, the lights are really bright, so I can't see you. Maybe that'll make this easier. Hey, my name's Mike, and this is my 5th appearance at PHP UK, so thank you very much to the team for inviting me back. Hopefully I'll make another one. I'm the CTO at Stuents.com, which is a UK-based prop tech company. If you want to connect with me, the best place to find me is at m1key at the phpc.social Mastodon instance, or wherever you are on the Fediverse. And today my talk is Beyond Relational, Data Storage for Modern Applications. We're going to be talking a lot about databases. We're going to have opinions about databases. Some of you are going to disagree with those opinions about databases. This is OK. We're going to talk about a range of different data storage technologies, and we're going to clarify why we're talking about them in a moment. But first, relational data. Where were we starting with relational data? Because that is where we all tend to start. I called this talk Beyond Relational, because it was a sort of predetermined thing in my mind that you would know what a relational database was. But have you considered why you're using relational databases? Well, maybe it's because they're widely available and understood. The chances are, if you started using PHP as your first web language, you were guided into some sort of tutorial that maybe used it in conjunction with MySQL, or another SQL database flavor. If you've used WordPress, or Drupal, or any popular framework, CMS, Symfony, Laravel, you have also most likely been guided into using a relational database. And it is true, a relational database tends to do most things we want. But is that a good enough reason to use them? Are we using them because it's the way we do it? Abraham Maslow said, I suppose it's tempting, if the only tool you have is a hammer, to treat everything as if it were a nail. Are we busy using our relational databases, treating every problem the same, because all we have is a hammer in the terms of our relational database? Now, I want to clarify a few things to prevent some sort of wave of anger or judgment from coming on me at the end of this talk. Using a relational database is OK. This is not a talk to tell you you're doing it wrong. There is no need to leave this weeping and rebuild your entire application around something new. In fact, many use cases are best served by a relational database. But we here are engineers. We should apply all different knowledge to a problem and figure out the best way to solve it. That means knowing there are choices beyond relational databases and working out whether those might be best suited to our use case. And also, I'm quite into AWS, so I'm sorry if other clouds don't get quite as much of a mention. Some of the things I'll talk about with AWS do have parallels in other clouds. Other things just don't. I'm going to talk about mainly what I'm experienced with, because I think that's the best thing for a speaker to talk about. But if you want me to talk about Azure, GCP, or anywhere else, please come and chat to me afterwards, and we can try and figure out where what you know aligns with what I know and find a happy middle ground. If we're talking about the principles we need to understand, we need to define what those are. What choices are we basing our question about databases off? If we don't know the things we're deciding on, we're not going to make good decisions. And firstly, I want to say size is a relevant metric. I don't know each of your companies, each of your use cases, each of your user bases. The chances are, in this room, in a room this big with this many people, and people watching on the live stream as well, those use cases will be quite diverse, quite different. There'll be people here at large enterprises, and people here who are just starting out, people here who are making hobby projects, and people here who are building the next piece of cutting-edge technology. But in an application with low usage, infrastructure choice often isn't so important. You can generally do whatever you want to do with whatever you have in front of you. Once again, the hammer and the nail analogy. And by usage, I can mean frequency of requests, amount of data stored, or both. If you're storing a small amount of data infrequently used, you can do most things with it in whatever platform you want. But it does become important with growth as to what systems we've chosen and why we're using them. If growth is rapid, the time to implement might be short. The time to change course is often 2 weeks behind us at the point we need sudden increases in scale. For those of you who were here for Matthew's talk just before, he made a number of references to the fact that although Lambda can scale up to 1,000 requests a second, the big bottleneck in your application is most likely to be your database. And this is something you often need to think of ahead of time. Before you get that Hacker News or that Channel 1 French TV or whatever it was you mentioned, effect, before all that traffic comes to your website, you need to know what usage your system is going to be put to. And so I have 3 principles to talk about. The first is flexibility of storage. Store data as required by the application without having to remap or redesign storage. It's hard to move data from one place to another if you haven't planned it in advance. Portability of data, be able to transform data at will to meet new goals, unconstrained from hardware management. And finally, looking at the boundaries. Which things are we storing in our database that are actually data? Data relating to our business, our use case, our domain, for anyone who attended Rob's talk this morning. And which things are infrastructure? Things in our database that actually are about how our applications work, rather than what they're doing with the data. Firstly, we'll look at flexibility of storage. Our businesses are going to grow. The chances are new business goals will tend to mean requiring to store and analyze more information. That might be more in terms of volume. It might be new types of information, or just analyzing it in different ways. Generally, as a business grows, data in some way will increase. The scope of entities expand. That means new fields are needed. And we can represent these as new columns in existing tables in a relational database system. Or we might want to add new tables and build out relationships. After all, we're using a relational database. Here's an example for a new column in an existing table. We have a new requirement, some new data to store about our user, and we add a new column. Nice and simple. But we can end up with databases that look a bit like this. So big and so many columns, they overflow the edge of my slide. And at this point, we start losing track of what data is in our database. And we start having these rows that look incredibly anemic. A row might have 50, 100 columns, and in any row, most of the columns are null, or empty strings, or 0, or the really fun thing that dates do, where they go 0, 0, 0, 0, 0, and then become 1970 when you actually render them. We can also do new tables. We have one existing table, and we add a second table that joins to it. That's a nice, easy relationship. Again, relational data. And we can add another one. And then we can keep adding them until our structure looks something like this. And it becomes a little bit hard to see how everything is working, how everything connects to each other. Imagine you're a new engineer, and you get shown this. And this, honestly, would be quite nice for a new engineer. The chances are it's 100 times this size. It can be complicated to represent data in a relational format, because how we tend to think of data is not in relational tables. We think of it in objects. Most of our applications are based on objects that interact with each other. A user adds a product to a cart and checks out, makes a payment. All of those things are entities, objects that interact in our system. And joining tables, which is what we demonstrated before, can achieve expansive systems. But this relies on heavy coupling between our tables, complex queries, and a knowledge of how those relations persist through our system. If I have 2 tables and I have the same key in each one, are those related? Is it allowed to not have that key in this table if I have it in this table? But in this case over here, it has to be there, but in this case, it doesn't have to be there. So is that key allowed? Is it permitted to do this? But this old data doesn't follow the rules of the system at all, because it's legacy, and we change the system afterwards. When we interact between our front and our back end, though, we don't tend to have these problems. Most of you, I will guess, are building front ends that will send JSON payloads to the back end in the form of user data, or maybe form submissions. And in the majority of cases, you're returning JSON data to your front end to render to users. This is how you're displaying the entities in your system. And so structured data like JSON offers us a lot of flexibility in how we store data. In this case, we have let's imagine we have a taxi app. No one's built one of those yet, so maybe we'll make one. We have a taxi app, and we have someone called Alice, because you always have to have someone called Alice in computer science demos. And we have a list of ratings. And we can see, actually, the history of our application as we've thought about ratings over time. In the first case, Alice got a 1-star rating, which wasn't very good of Alice. Needs to do better. And then the second time, our developers decided, well, giving Alice 1-star feedback without any reason wasn't very helpful for Alice. How are they going to improve? Well, in the second one, they get 2 stars, and now there's a reason. The user has said Alice was speeding. But in the third example, our developers have decided, actually, we need to give even more information. We need a detailed breakdown of this rating. And so we're giving efficiency of 3 and safety of 4, which is ironic if they're speeding. But our schema has changed over time. We've added fields, and we've even changed the type of a field. Stars has gone from an integer to itself a nested object. And our ratings is itself a list of objects. Mapping this in relationships in tables would be complicated, especially with the history aspect. And so we have document stores, where we actually store our data as entities, just like we represent them in the rest of our application. A popular document store is MongoDB. MongoDB stores JSON documents in something called collections, which are sort of equivalent to tables, but for good reason, it doesn't call them tables. We should think of them like tables. They're collections of documents. Mongo supports indexing and transactions, things that you're used to from your relational databases. You can write multiple rows to it, or I say rows, you see that's even relational language creeping in there. You can write multiple documents, and if one of them fails, you roll back transactions. You can index on certain fields you want to search often. Mongo can aggregate data for you, so do sums over collections, or run internal JavaScript functions. This is kind of like SQL stored procedures, except it's in a language your engineering team probably already know, which is helpful. And Mongo uses a programmatic API of our language extension, so there's a xmongo for PHP that you can use to interact directly. This example is cribbed straight from the Mongo website, so it is in JavaScript, but the PHP format would be very similar. You insert an item into a collection, and it just looks just like your JSON document before. Similarly, you can do a query to get data back out of your system. The query here isn't in SQL. Once again, it's a JSON object. It still uses a domain-specific language. It uses its own formatting. You have to know that GT is greater than for a search. But this is also quite user-readable, potentially more so than SQL, which often, if you're trying to build a query out of SQL, you need to use a query builder that someone's already built to put the language together for you. Whereas in this case, anyone can see how they could construct that object. And if we run this query on our Mongo database, we get our data back. Our user comes out, and in this case, they ask for a projection, which only limits the amount of data returned. So you only get the specific parts of the object you want. A document store means we can store data in the same way the rest of our application is used to using it. Related to document stores are key value stores. And this is a type of database, even more basic, as it were, than document stores. A key value store will generally have a single key corresponding to a single record. With our collection before in Mongo, we could say, I want all users with an age greater than a certain value. With a key value store, the only way to access an object in the database is to know its key already. This serves excellent use for things like caching. They have generally very fast lookups. The key value store will have limitations if you want to just find some data in the whole store, because you have to know it's there in advance to look it up. But a great thing about a key value store is you can cache generally anything under a single key. 2 different keys can have entirely different data. You can overwrite the value of a key with data of a completely different type. A lot of them will allow text data, some may allow binary data, and you can generally put whatever you want at each key. A good example of a key value store is Redis. People might have come across Redis. It is very commonly used as a cache, but it can actually do a lot more. It's got a cool feature for caching where it saves the cache to disk. And again, in the previous talk, a lot of mention of cold starts. You get the same thing with caching systems. You get cache warm-ups that you might need to do when a system boots. Redis can actually save your cache, store it to disk, and then load it again the next time. It can send cache proactively back to your services as a message broker. And a very useful thing for caching, it can expire your cache. So if you are regularly querying, and this is where Redis can fit into even a relational system, if you're regularly querying users for maybe a user's password or some sort of login token, you can say, well, actually, let's store that token in our Redis cache for 10 minutes. If the user's making lots of requests, that's still going to speed up your site. You don't have to go to a database each time. You can go to your cache. But you expire it in 10 minutes, because maybe within 10 minutes the user could have changed their password, and 10 minutes is an appropriate time to keep them logged in if they have. Redis also has access control for different keys, so you can sort of segregate parts of your application. And it's got a command-based API. So in PHP, we have another extension. And here's just a few examples of a Redis caching system, where we are able to set cache values into Redis, and we're able to get them. I decided to make my getter a bit more interesting, and it has a callable that will actually get the object for you if you want. So imagine here we put this in front of a database. That callable get could be a function that calls our database, it gets the item out of it, and stores it in the cache for us. And this is all done in a very simple format. There are also, if you're doing caching, there are PSRs for caching that kind of indicate common interoperable types. We've had document stores. And we've had key-value stores. And a question might be asked is, why can't we have both? Well, we can. Amazon's DynamoDB is a hybrid key-value and document store. And it's got no infrastructure to manage as well. In a way similar to Redis, it can expire rows via TTLs, so you can set a time to limit value. A heads up on that, the TTL isn't exact, it's sort of best effort. So we have found that with very large tables, the TTLs can take longer to run. That can be important in certain use cases. It can also use a stream to stream out what the database is doing to provide secondary processing, and we'll address streams a little bit more later. Now, I say hybrid key-value and document store. That sounds a little bit strange, but I'll try and explain it. There's probably enough in Dynamo to do a whole talk on it, but I'll give you the rundown and you can explore it later or talk to me if you want more information about it. Dynamo has a composite key system, a hash key, which acts like SQL's group by, and a range key, which acts a bit like a SQL order by. In this case, we're storing data for users via their email address. Maybe we're storing data of submissions to some sort of competition. And user@email.com has submitted one entry from Manchester, and they've submitted it with a certain date and time. And they've done another one from Amsterdam a day later, so clearly they're a bit jet setting. And we can query this via the two keys. If we know the user's email address and the date and time of submission, that is our entire key. That's our hash key and our range key combined. And so we can do a query, and this is just like a key value lookup. We'll get our one row back from our hash and range key. In Dynamo, a record is uniquely identified by its hash and range key. So if you write to the same hash and range key, you're writing the same record. It doesn't have the concept of an insert versus an update natively. You can sort of apply this on top of it. But if you write to a key with the hash and range key together, you write a single row in the table and overwrite anything that's already there if there is something already there. But this means it's got a fast response even on massive tables. So a huge table of data, if you do a query with a hash and range key, you will get your data back incredibly quickly. But going further than the regular key-value store, you can also query on just the hash key. And when you query on just the hash key, you get back every item with that hash key, regardless as to what the range key is. It's still a very fast response. This one is paginated, so it pages in groups of 1 megabyte. So it's not a number of records, it's a record size limit of 1 megabyte, and then you can page through them. The default SDKs for things like PHP include an iterator, so you don't have to think about that, which is really helpful. And in this case, we can see that we can search our user's email, and we see all these different records that they've put into the system. This is really useful if we want to look up everything a single user's done, but also be able to look up one row. And you can combine these in really interesting ways. Dynamo also has global secondary indexes. So if you realize later on in your application, or even at the start, that you need a different access pattern, then you might want to put in a global secondary index. In this case, we've realized that we want to analyze some information. We want to know what domain name users are coming from. This could be useful, say, if our competition submission system was based on companies. You would have your company email address. And we want to know everyone from your company that's signed up or sent a submission in. In this case, we're going to do two things. Firstly, we're going to denormalize our data. In relational database terms, you don't tend to denormalize data. You tend to keep one field in one place. If you need that field from somewhere else, you join onto it, or you query it, or you use some sort of projection of that field. But you don't replicate it in your database. That would be seen as the wrong thing to do in most relational systems. And Dynamo actually encourages denormalizing your data. Split your data into lots of different parts, because then you can do more interesting queries on it in the future. In this case, we've taken our user, and we've split their email address into domain and prefix. We've made domain a hash key and prefix the user. Now we can check every instance of a single domain, or every instance of a specific user and that domain. And here's how we do a query in Dynamo on that email address, that domain name. And we get a list back again of all the people with that domain, and we can see actually that there was a user we haven't seen before. We've got 3 user ats, but 1 test at. Very imaginatively named data. And so the same values can be the case for these records. You'll notice that there are 3 instances of the hash key email and the prefix user at. So unlike with a primary index, secondary indexes don't have to be unique. One thing to caution with Dynamo is if you start putting data into Dynamo and then you realize you need to have a hash and range key combination for every possible pair of columns, your Dynamo table is going to get quite expensive. Because the way Dynamo does this under the hood is it stores your data once per index. So if you have 20 indexes, then your data storage cost is times 20. Your write costs will also go up by times 20, but your read costs won't. Your read costs will just read off the index that you're reading from when you do a query. So that's something worth bearing in mind. It's not something that you can just do every possible thing in. You have to think a bit more about your use cases before you build your database than maybe you would in a relational system. But in exchange for that, you get a very powerful, incredibly scalable system. And that brings us on to the idea of portability of storage. Data unconstrained by infrastructure. There are some common infrastructure constraints. As I say, Matthew already alluded to them in his talk. High usage in one area of your site degrades areas in the other. So you have, again, the Hacker News effect. Loads of people on your main page of your site, and suddenly your staff are unable to carry out their operational business because it uses the same database, and that's just gone down from all the pages you're trying to serve. The way to fix this is to over-provision. Okay, so we're on Lambda now. We're not having to provision any web servers, but we've got this enormous, beefy, 16-core, 200-gigabyte database server just sat there serving one query every 5 minutes, just in case that one time we need to serve thousands all of a sudden. And data tends to be locked in one storage medium. We've chosen a place for our data, and we keep it there. This isn't just relational either. This can be wherever we go. If we think about just a single database, if you go and translate what you've got with the relational database into Dynamo, you have the same problem. You still have hammer and nails. And so you end up with trade-offs between operation of your system and analytics, things that you want to analyze about your business, things you want to check out that go beyond the normal day-to-day queries expected by your application. And relational databases do offer some tools to help in this area. Read replicas are a good example. If you are using a relational database system and you haven't tried out read replicas, they're a great way of splitting load. You can tell your application that certain queries should go to the read replica. You can have your back office analytics go to a read replica rather than a live system. Do be aware of how much you use that, because read replicas sometimes can lag in terms of where the data is. So I wouldn't use it to check if a user's payment has gone through yet. You'll still need that in your operational system. And they also add extra cost and complexity. You now are provisioning extra read replicas, which is just sort of the same over-provisioning problem, just shifted to the side. Another way we can do this is alter our application. If our database is slowing down all the time, we'll fix the queries that are causing the database to be slow, add some more indexes. There's probably ways you can do that. But once again, you're sort of constantly chasing these performance issues. You're constantly trying to find another performance issue, and then behind that one there's another one. And so an advantage for this can be going serverless. Serverless. Because as Matthew's already mentioned, if you don't have to think about the servers, then you don't have to worry about how much they're up, how many CPUs they have, how much memory they have. And there are different choices for serverless databases. We have PlanetScale, which is SQL with sort of some limits. It's got a few strange things around the engine it runs. Google Spanner, which is semi-serverless. You do still have to provision it, but it can scale very quickly. AWS Aurora Serverless, which is serverless, but it can't do the one thing serverless is really good at, which is scale to 0, so you're always paying a bit of it. And those top three are all still SQL relational database systems. We also have MongoDB Atlas. We talked about MongoDB as a document store. Where using Atlas, you can run that serverless. You don't have to think about the infrastructure you're provisioning anymore. And finally, CockroachDB. That's a database I have no experience with, but I'm told it's serverless, and that seems kind of cool. And it's also got one of the weirdest names of any database. And of course, DynamoDB. I am a bit of a fan of DynamoDB. In on-demand mode, which is sort of the default mode now, I think, for Dynamo, it will scale from 0 to 3,000 requests per second without any throttling. If your application is doing well enough to go from 0 to 3,000 requests per second, well done to you. You have a very successful business or just really good SEO. It can also scale up to 40,000 reads or writes per second, given time. So if you really need to ramp up to an insane amount of traffic, you've got to give it a little bit of time. Or you can tell Amazon in advance, like you can with Lambda, hey, I think I'm going to need 40,000 requests a second, and they will gladly charge you for it in advance and provision it for you. In on-demand mode, reads, which are 4 kilobytes in data size, are priced at 30 cents per million reads, and writes are 1 kilobyte per 1.4 million. Just remember that earlier from our indexing, that reads will read off one index, writes may write to multiple indexes, depending on how you have your system configured. Now, as well as choosing a serverless database, we might still want to do things we can't do in our document store, in our key value store, in Dynamo, or even in our regular SQL system. And this is where the principle of ETL comes in. This stands for extract, transform, and load. This means we want to move data from one place to another. And this can be done via a few different things. We can have data storage, which is either built into the storage. I mentioned before with Dynamo, a cool thing is there's a stream going out. So every time you change data in Dynamo, you get a write to a stream, which you can pick up with something like Lambda, and then do something based on whether data was added, inserted, so added, updated, or deleted. This also powers something which Rob mentioned in his talk, which is CQRS. If you want to segregate your application so that you can have commands served by one platform and queries served separately, it's a really good idea to move data between those platforms as well, so that each system has ownership over its own data. A danger of not doing that is the big ball of mud system, where your commands and queries are so tightly coupled to your data that there's not much point splitting them in the first place. And transforming data means we can do different things with it. We can change from an object to relational, or even columnar storage, where we aggregate lots of data in different formats so that we can serve the best use cases. An example of a place where using a data stream and writing into secondary storage for different use is really good is when you use Elasticsearch. Elasticsearch is document storage, so JSON documents, but it's adapted for full text search. You can do really cool stuff with Elasticsearch, like fuzzy searching. So you can search all users with gmail.com, and it will also find that one user who always types gamil.com. And it will give you a list of all the results it has, and it will give you confidence scores. In our own business, which is PropTech, we use this to identify strange spellings of road names. We also use it to identify strange configurations of postcodes by looking at this thing and saying, if there's not something with confidence 100, is there something with like confidence 50 that is the first result in the list? Maybe the user's just got their postcode wrong. It's accessed via HTTP API, so it's really easy to hook any application into. You don't have to write drivers. And it integrates also with Logstash and Kibana. So actually, Elasticsearch, many of you might know as part of the ELK stack, which powers a lot of analytics and monitoring systems. As I mentioned, it provides fuzzy search with confidence. And just like I mentioned before with Dynamo, Elasticsearch works really well if you're happy to denormalize your data. As you put your data into Elasticsearch, let go of all those things in the relational world that tell you to not store the same data twice. Store the same data in like 5 different ways, and Elasticsearch is going to serve you much more effectively by finding interesting things within your data. An example of an Elasticsearch query might be this. So we're trying to find the phrase Alice in our drivers list, like we were before. And we get a result back saying how long the request took, how many records we actually touched in our database, and how confident it is. In this case, our max score is 67%, which isn't particularly high confidence. So maybe there wasn't an Alice, but there was an ally or something. And that person has a 67% score and an ID of that record. If we decide that that's the one we want to choose, we can fetch it. In this case, we might say to our application, if the score is over 75%, just render that one row. If it's below that, maybe give the user a selection of different options. Another system that's really suitable for ETL-based workloads is Snowflake. This is where we go from operational data into what we call data warehousing, storing all your data for a very long period of time, often in huge quantities, and to do big analytics things with it. You're rarely going to expose your data warehousing to your customers, but you will often be serving internal users with it. With Snowflake, you get elastic scaling. It's not serverless, but it does scale very fast up and down. If you know that your quarterly reports are coming up and you need to run some big queries, you can scale it up quickly, run those queries, scale it back down again to save yourself some server costs. It will work with structured, semi-structured, and unstructured data. So it will work with your JSON records, it will work with CSV files, and it will work with just random text that Bob from accounting insists on mashing stuff into. It also has historical search. This is a really useful feature that isn't often thought about with databases. We often overwrite data in our database, and that data could have been useful. And now we can handle that with things like SQL triggers or with triggers in things like Doctrine, but we have to think about it up front. And often, by the time we realize we overwrote some really useful data, it's too late. We've lost it. Maybe we have a database backup, but restoring from backup to analyze some data seems really awkward. Snowflake deals with this by keeping historical data. As data changes, Snowflake also knows the history of that data, so you can do a search throughout your history of your data. And it has relational data. Some people are just comfortable in a relational world. They've learned SQL. They are really confident in it, and we don't want to say you can't use this. But they also might be the case that you just can't use relational data in some formats, and so this is an option, not a requirement. A cool area with Snowflake is getting data into Snowflake. Often when we look at things like ETL pipelines, one of the things that blocks us from doing anything is the workload up front. Elasticsearch was a good example of this for us. When we initially started trying to ingest data to Elasticsearch, as a team who hadn't used Elasticsearch before, the process of taking data from a place we knew and putting it into Elasticsearch was incredibly hit and miss. It involved us repeatedly having to wipe all the Elasticsearch indexes and rerun a process, only to find that after 3 hours it would fail or something, and then we'd have to wipe it all and start again. It wasn't a particularly fun process. I'm sure there might be experts in Elasticsearch who would tell me I was wrong and there was a tool I could have used. But as a team exploring it, it wasn't particularly obvious. With Snowflake, there are built-in options for data loading. It wants to take your data in the nice way. That sounds weird. It has built-in options. It's got bulk loading, so if your data's in something like Amazon's S3, Google Cloud Storage, or whatever Azure does, it can take that data. You can also just load it from files uploaded to some sort of server. It has Snowpipe, which is a pretty cool name, and it's nothing to do with extreme sports, which can continuously load data from other systems. And if you're using Kafka, which I'm guessing some of you will be, for streaming data already into an application to build things like event-driven architectures, Snowflake can pull data out of your Kafka stream as well and just ingest it straight away. That's a particularly useful one if you are using event-driven architectures, because you can just pull whatever happens to be in your stream into Snowflake and analyze it later whenever you need to. And finally, relational databases. This is outrageous. We come here to hear about not relational databases. Why are you telling me I should use a relational database? Well, the thing is, as part of an ETL system backed off something like a document store or a key value store, a relational database can actually be useful. You actually remove some of the restrictions of relational databases if you see it as a secondary store for your data. For example, you can redefine schemas. You can say, oh, the schema's rubbish, it's not right, we need to change this from multiple fields in a table to multiple tables joined together, and you can just rerun your data through it and build that view again. This is especially useful if you're doing something like an event sourcing system, where you often want your projections or your aggregates to be captured and updated in real time. And so you can also choose multiple views for different use cases. I can stream my data into 3 different SQL databases and format it 3 different ways for the best query performance. And in my business, we actually do this. We have a separate set of Aurora serverless databases that we stream data into from our main application in order to view it in a different way and do different types of queries on it. It's really useful for that. And we use serverless there so that if it sort of needs to do massive queries all of a sudden, it can scale up for us. And when we think about how we move data between systems, especially into other relational databases, and maybe then from there into other relational databases, and from there into Snowflake, and into various other places, we do get a bit worried about the boundaries between our application. I mentioned at the start that sometimes we have to think, where is the gap between our data, which represents our business, our domain, our customers, our users, and our infrastructure, the thing that makes everything happen. And as I mentioned before, we have the Maslow quote, the hammer and the nail. If you're building a system and all you have in front of you to store state is a relational database, is it any surprise that elements of our implementation, our application logic, will bleed into this? Have you ever seen an example like this? Select all from jobs, order by added and ID. We have a jobs table. We have a date that the job was added. We have some data, JSON. And we have a completed date, which is either a date, time, or it's null. This is likely to form the backing of some sort of job queue, a process within your system that does workers. You have a worker maybe running on a cron that says every minute or every 5 minutes, I'm going to check all this data from here, and I'm going to run some jobs. I'm going to run whatever data they've given me with whatever job I'm being told to run, and then if it's done, I'm going to mark it as complete, and if it's not done, I don't know, maybe I'll log an error somewhere, or I'll just leave it for the next worker to run, and we'll handle that over time. And over time, this data becomes a little bit strange. It becomes huge, unless we start clearing it out, and it leaves a lot lacking in terms of our infrastructure flexibility. One thing, application processing, the way our application works, now depends entirely on the availability of our storage. This means a busy database, things will process slower. During that busy time, when you're taking loads of orders, you also now lose the ability to process orders in your worker system because your database is too busy. It requires custom monitoring. Databases are not generally designed for this purpose. They are to store data. They're not part of your application infrastructure. So the monitoring around whether those queues work will need to be built by your team. And it's a bit of a sort of quantum problem of by measuring how many jobs there's to do in your queue, you yourself are doing a read operation on your database and affecting the performance of your database to serve the queue that you're trying to monitor. It's a bit difficult. And it reduces the flexibility of your process management. If you want to change the way your queue works, you now rely on database schema changes. What about rows already written to the database? How do we handle those? Suddenly, you've mixed two things, and you get to a bit of a problem as you hit a certain point of scaling. And again, it is worth re-mentioning. At low scale and small applications, this is probably not an issue. This is probably a really good way of doing something. But in many applications that you're building, you don't know when you're going to hit that high scale. Maybe you think you never will, maybe you never want to, but you might at some point. It's worth addressing this early on with things that are still good at low scale. And so we come to queues. Queuing systems to get your data in order. Queuing system has a few features that make them very suited to the idea of running workers. They're also suitable for other things as well. A great part of a queue is exactly once delivery. With certain queue systems, you can say a message in my queue must be delivered only once, and the queue will respect that. This means that you don't have to have some sort of check in your job to say, oh, has this already been run somewhere else and I need to check first by checking some field somewhere else on another table, or checking if this email was already sent and when do I check if it was sent, all this sort of complications. With queues that can deliver exactly once, you often have what we call a visibility timeout, an amount of time your worker has to respond to say, yep, I've got that message, I've handled it, until the queue decides, actually, maybe it never got it because of a network problem or the worker crashed, and then lets it go to the next worker in the queue. Most queues will have observability, built-in metrics, part of the system. Because it's designed to be a queue, most queuing systems will tell you how they work. They'll tell you what the current throughput is, how many items are waiting, how many items are currently being sent to consumers, what the rate of input and output of your queue is. I've put these two together. High throughput, you will generally want to make sure your queues can handle lots of processes going in. So if you're writing those jobs, you need to be able to handle lots of ingest. Even if your processing with workers is like one worker just chugging away, doing one job at a time. Queues are ideal for cases like webhooks, where if you want to do payment processing, you might get hundreds or even thousands of webhooks across a single minute into your application that your application can't handle. But by putting them in a queue and letting your worker just slowly chew through them, you reduce that upfront load and you spread it out over time, and hopefully please whatever system's sending you webhooks by not sending them 504 gateway timeouts. And finally, scalability. If you are using a queue and it has high throughput, it should be scalable as well. Once again, we don't want to over-provision and spend loads of money on a queue that's sat there doing nothing. A great example of a queuing server is RabbitMQ. It's a message broker, so you can actually have it not only have someone ask for items in the queue, but it can tell someone that there's an item in the queue and send it to them. It can set up routing, so you can say if a message looks like this, send it to that worker. If a message looks like this, send it to that worker over there. So it's handy for building sort of, especially like microservice style systems. It communicates via AMQP, which is a custom queue protocol, or just HTTP, so your existing applications can already hook into it. Once again, we've got serverless, and we have Amazon's SQS, which is a serverless queue system, which is purely HTTP, and it has really good first-class integrations with things like Lambda. So if you are using Bref, you can hook your queue directly into Lambda without having to worry about setting up some sort of system to poll it on a regular interval. It will just send items into Lambda whenever it can start a Lambda up. It has two modes, a regular mode, standard, and first in, first out, FIFO mode. In standard mode, it will deliver all your messages. It may sometimes deliver your messages twice, and it will sometimes deliver them out of order, which could be fine depending on your application. But it also has a FIFO mode, which is much more strict, and it will deliver your messages in a sort of exact order they go into the system. And it will also make sure that a message doesn't get sent twice. One thing that people often talk about with queues, I've seen this on social media a few times when people kind of get at the teams designing SQS and other queue systems, is the ability to see what's in your queue. This is quite a common thought. If you've got like a job queue in SQL, you can generally say, OK, I know what the next job is in line, but what's the 29th job in line? And what's the one after that? And actually, what's the one at the end of the queue that's going to be processed last? It's a perfectly natural thing to want to ask. A lot of queues, however, don't allow this. You can't go to SQS and say, hey, I can see you've got 200 items in the queue. Can you give me the 50th, please? It won't do that. It will only give you the next item in the queue. And I've seen a lot of people complaining and saying, no, I want to see what the 50th item is. And it's a really interesting area where the developer experience of what we want out of our system competes directly with the reason for using a system. In a queue system, the whole point is to deliver messages in an order. If I provide an API to you to say, OK, well, normally you get them in order, but for moderating your queue, for sysadmins, you can check the 50th item. Go on, I'll let you. You can guarantee that very quickly, someone somewhere will make a system that uses that API to pull the 50th item out of your queue and runs it separately. And then that item runs again later, out of order, and duplicated. And it's an interesting area where sometimes being constrained, having a limit placed upon us by the infrastructure that we choose to use, is actually a good thing. When people complain that the queue works in a certain way, I often look and say, well, that's why you're using a queue. You want to follow these rules. You want your application to follow these rules. A common argument might be, well, I can do what I want. I can think about how I operate my system. But in some of these areas, we don't want to be constantly looking over our shoulder, constantly reviewing every pull request to make sure it's working exactly the way it's meant to in case they do something they can't do. It's actually quite a luxury to have some control taken away from us and a system just to work in one way. And that means it's predictable, especially at scale, especially as we build our companies and scale up our businesses. So that's a good thing to mention about queues, because I've seen that mentioned quite a few times before. In Amazon SQS, we also finally have a dead letter queue. This is really useful if you send your item to a worker and your worker crashes. There's a weird state where that item's out of the queue, but it's actually not done yet. And sometimes the queues will just bring them back and try again. But the danger there is that you could duplicate the processing. Imagine if your worker has sent an email to a user and then crashes. Now your user keeps getting email because that worker keeps sending the same message. The dead letter queue means that after a certain number of tries, ideally like one try, it drops the message into a second queue, which is there to be looked at by your own team. And that way, your own team will repeatedly run that queue to check what's in it in order to assess what's happened. Maybe there's an error logged. Maybe they need to fix something and rerun it. Maybe they need to check if it's done all the things it's meant to do first. So you can end up with some quite interesting systems once you start building into a queue. And to finish, I began at the start by saying I had some general principles. And so I've got a highly opinionated summary. You want to prefer tools with low infrastructure management or expertise required. Hopefully that's come across in the times I've talked about things like serverless. In our small companies, we probably can't afford to hire a DBA and someone to run all these different queue systems and streaming servers operating on Kubernetes and everything else we need to do all these different systems. We want low infrastructure management expertise required, and that means that anyone in our engineering team can expand their knowledge of infrastructure and build things that are useful for our businesses without having to say, oh, can I provision that? Can I use that? Can I use that server? Can someone spin that up for me? Can someone create that? I've created it and it keeps crashing. Can someone go and fix that for me? Maybe controversially, vendor lock-in, I think, is a price I'm willing to pay. Things like DynamoDB, like SQS, and their equivalents in other clouds might, to some extent, lock you into their service. It might make it harder to migrate off their service. But let's be honest, if you're storing your data on those platforms anyway, you're already locked in. Data is generally really hard to move, especially massive databases. In fact, by building across these different proprietary or hosted database services, but building with a mindset of using streaming, using ETL systems, you can actually migrate much more easily. You can set up a system where you can slowly trickle data into another service over time and eventually switch over when it's convenient. So using a proprietary system, A, might not lock you in as much as you think, but it also might be a worthwhile price to pay for the convenience you get of someone else and something else managing the way your system works. So systems are easy to migrate. I can run my code in anyone's server hosting, but data is generally not. So I'd pick a service that offers good flexibility. And finally, match your application to its data storage. If all you've heard from this is that you should be using a relational database like you currently are, that's great. You go away today with more assurance that you're doing the right thing. Whereas if you go away thinking, oh, goodness, all of these challenges are challenges I've had with my application, maybe even this week. Our database has crashed this week, or our read queries are super slow this week, and people are complaining about them. Hopefully you've heard something in that format that says, oh, maybe if we use this service or this service, we can start to resolve that. But again, make the same decisions. Don't just walk away from this and say, well, this guy on stage said to use Dynamo, so I guess that's what we're doing now. Make those choices around your application and your knowledge. And finally, a rundown. I promised this would be all about data storage, and I don't have time to cover every possible means of data storage. That would be a little bit crazy. But there are other more niche data storage solutions that I thought it's just worth saying out to a room of people, because someone somewhere will think, oh, that's the right solution for me. And at the very least, you'll have a word or a phrase or a company name to go and Google, and then find it and learn more about that afterwards. So hopefully some of this is useful to people. I have some knowledge of these, but not nearly as much as everything else I've talked about. But please do come and chat to me, ask me if there's any particular weird and niche use case for a database that you have. I'd love to hear about it and add it to my talk next time. So graph databases. These are similar to document stores, as we've already talked about. They often store JSON-based data. But a graph database is sort of unique in that a relation is a first-class citizen. So in a relational database, we'll have this table, and it'll have a foreign key relating to this table. But it only has a foreign key to this table. Or maybe it has two foreign keys to this table and this table, but those are fixed. This table always relates to the same number of tables, which works for a lot of use cases. But a graph database allows any entity in the collection to link to any other entity. So I can have a customer which links to maybe their cart, which links to their orders, which links to some payment that was made, which links to some reviews, and those can all just be related in this graph. Graph databases are especially useful for things like social networks, where people's relationships between each other are nuanced, so you can label your relationships as different formats. And so they're sort of like foreign keys on steroids. And some examples of that, Neo4j and ArangoDB, who have an avocado as a logo, which I love. Time series databases. These are single purpose. These are very niche in terms of like there's pretty much one thing you tend to use them for. They're for storing time-based data. This could be part of your monitoring system. Just like the ELT stack is a database that's part of your own monitoring system, time series databases could monitor the response time of every page on your site, and it logs it to a time series database. And that could be a huge amount of data. In fact, for some time series databases, that would be not enough data to justify them. But I've seen them used for things like click tracking, so like track a user's mouse movements around your site and like respond to put a data item in every time they click. That's the kind of thing time series databases are good at. Also, IoT. So if you're doing anything with like sensors, time series databases are great for storing huge amounts of time-based data. So they're often optimized for really high throughput. You can put lots of data into them and they don't fall over. And they can do calculations over time. So you can say, what's the average temperature over all these millions of sensor readings from around London over the last 3 years? And you can find a trace of that. The only example I have for this one is InfluxDB. I know that someone in this conference used to work for InfluxDB. I don't know if they still do. Maybe there's more. And finally, I have to mention Quantum Ledger. I'm sorry if I'm coming across as an AWS fan here. I'm not paid by them, I just use their services. But Quantum Ledger is a niche database that I really just don't see any parallel for in any other cloud or any other data storage system I've seen. It's a document store, just like a lot of the other things we've looked at. But it has table semantics, so you have a table, the table has indexes, so it's got a sort of vague SQL-ness to it. It uses a sort of custom SQL dialect to interact with it. The interesting part about Quantum Ledger, and the word quantum in the title is completely misleading, by the way. I did a talk about Quantum Ledger at an AWS event last year, and loads of people turned up hoping to hear about quantum computing and were really disappointed that I was talking about databases and JSON. So Quantum Ledger has nothing to do with quantum computing. It's classic Amazon naming. But it uses a journal to track changes. So as you write to your database, every operation is stored as a new item in a ledger describing the history of your database. And as part of this, it writes a hash for every single entry. These hashes are connected in a chain. One could call it a chain of blocks, or maybe no one's heard of that. But they're cryptographically verifiable. So you can look at any point in your database, and then you can have a hash at any other point and say, has the data changed between this point and this point? And by changed, I don't mean someone's done an update on a row. I mean, has someone gone in to your rack server with a keyboard and mouse and plugged into it and got the encryption keys off the disk and edited that data? This might seem like intense paranoia. But if you work in something like fintech, this might be exactly the kind of paranoia you need. Protection from even the most insider of insider threats of someone on your admin team or someone in the data center itself modifying data. Because when you're storing something like a user's account balance, someone being able to add an extra 0 to the end of it is a pretty tempting target for your data. Quantum Ledger doesn't prevent that fully from happening, but what it can do is show it has happened. You can verify your database. We use Quantum Ledger for storing financial data, and we have a system which outputs the hash of the database on a daily basis into our Slack channel. Because the thought is that someone's not going to both hack our Quantum Ledger and our Slack at the same time and manage to guess the right cryptographically verifiable key to replace it with so we don't notice. We can then go in at any time and say, between these two dates, what was the hash verification? And Quantum Ledger will spit out a verification key. If that matches what we've got, then our data hasn't been modified. And as yet, no one has tried to insider attack our databases. I don't know if they ever will. I almost hope they will, just so we can prove this check works. And Quantum Ledger, just like Dynamo, can stream data to other services. It is a bit of a weird database to use for read operations. It's quite slow if you don't know the primary keys or index keys of an item of data, but it has a stream built into it. So again, AWS seem to be designing with this idea that you will store data in one place but stream it to other places. So we actually stream Quantum Ledger out to Dynamo, and then we fan that out to SQL as well to do different analysis on it. It is proprietary. There isn't really a comparison in any other cloud. The things you build in Quantum Ledger are probably going to stay there forever. It also has history. I realize I've got a bit of time, so I can talk about this. It has history, and I talked about history in Snowflake. Because you have this ledger of changes in Quantum Ledger, it stores the history of every change, which is, again, very useful if you are legitimately changing financial data, like updating someone's account balance, because you can see when it happened. So you can verify, actually, the history of your documents in Quantum Ledger as well. We've used that to debug issues when a production system just does the wrong thing. So it's a legitimate write from the platform, but it was wrong. And we can actually debug that and go, oh, this is where it was wrong. We can update it to the right value, and we know there was a bug, and we can fix the bug as well. So Quantum Ledger is really useful for that. If you're on AWS already, well worth checking out. If you're not on AWS, it might not be worth migrating for it, but who knows? And with that, my talk about databases and my love letter to AWS is complete. And so I'm going to bid you farewell and waiting for someone to come over to me and tell me to just use Postgres. Thank you very much.